Hi, welcome to Mathematics with Tom. I am Tom, and we're going to continue looking at linear combinations. So let's come over here, and this is our linear combinations. Continue. Linear combinations continue. And here's what we said. A quick review is always in order, and that was we said if we have, and before I even list these, let's just say that we have some vector x. Oh, I'm sorry. Let me do this. Let's do this. We're going to use our example. So let x equal, and we're going to use our same x that we did before, the vector 2, 1. And the vector y, we're still going to use the vector 1 and negative 1. And a few more things. We're going to say let C and D, we'll write it this way, be in the real numbers, meaning that they're scalars. So in this last bit, this is our third piece. And before I write that, if you recall in our last video, we said that if you take some scalar, C, and you multiply it by some vector, any vector, we'll call it V, that this creates a line in any space. So we'll just say in Rn. So what happens now when we have two vectors? Well, we can apply our principles of linear combinations. And that is our third one. So our third principle is this, is that if I have any vector v and another vector w in Rn, then what do we have? We can take a scalar c times the vector v plus our scalar d times the vector w, and here's what we get. We already know that c times v is c v1 and c v2 all the way out to c vn, plus we take d times w1 and d times w2 all the way out to the last component of our vector, d wn, and the result is now we just have vector addition. So we can say that this is just c v1 plus d w1. It's also c w2 plus, c v2 plus d w2 all the way out to that, adding the last components, that would be c vn plus d wn. So that's the general idea. This is our final piece of a linear combination. And what we want to do is see what do we create when we have two vectors that we can add together. So let's come back, and we're going to draw x and y, and then we're going to play with changing c and d. So I'm going to come over here, and let's make our graph fairly large. So here's my x-axis, and here's my y-axis, and let's just mark these off. I really only need just enough to get this started. Okay, so I'm going to graph. Here's the vector x. And then we also have the vector y, which is 1 and -1. So that's right here. Now, here's where I need you to follow with me. Because we're going to just do this as a thought experiment. A thought experiment. What we're going to do is we're going to do a few cases. So let's try this. If C, so we're going to look at C, oops, sorry, I want to use my white chalk and an eraser. So say we have the linear combination of Cx plus dy, and we're going to look at some cases. The first case is we're going to let C be less than or equal to 1 and greater than or equal to 0. Okay? So what happens in this first case? If I add these two, and let's also let d equal 1.
Well, let me stop you just for a second, sorry.
Yeah, I feel like I'm all over the place.
No, you want to use x, y because you're using v and w over there, or is that?
These were the general ones.
Okay, okay.
And those were
those are specific, sorry.
No, that's okay.
I just didn't know that, okay.
Is that what I wanted to do though? Hang on a sec. Okay, yeah.
I'm wide angle now so that we can see most of the board because you were referring back to the x and y, or do you want me to zoom in on you
Yeah,
now?
you can stay here now.
Okay.
All right, and let's let d also go from 0 to 1. Let's just see what happens. If c and d are 1, we've already seen this problem. These added to the vector 3, 0. And so I get this parallelogram and I pick up this point right here. Well, what happens now? What happens if I leave d as 1 and I make c a little shorter, or less than 1? Well, that puts c about here, or makes x a little shorter. If d stays the same, then I get a dot here. Well, let's make c a little bit shorter, and d at 1. And as I continue, what I get is I actually create all possible points on this side of the parallelogram. Now, this time, what if we make d a little bit shorter, like maybe right here? And then we run through the same process with c from 1 to 0. Well, what do we get? We create another line. And as we keep making d shorter and then running through the same process with c, we start getting all possible points that are inside the parallelogram. Okay, so then what we want to do is what happens then when c is greater than or equal to 1, and d is, well, we probably just need greater, but we'll just do greater than or equal to 1. Well, let's try this. We'll try this in our green. Well, again, when c and d are 1, we start right here. But what happens if this time if c makes the vector x longer? Remember, this can continue as long as we need to. If I take c here and I add 1 times y, what do I get? Well, I get this point right here. What if I leave d the same and make it c a little larger? And I get this point, and I get this point, and I get this point. And so pretty soon I get this line. Well, if I continue this process, then pretty soon, if I continue this process and I let d become less than 1, then I'm going to continue extending my parallelogram this way. if now I start letting d be greater than 1, then that means this vector increases. And if I run through all these iterations, what do I get? I extend this parallelogram out forever, and I get this region. Now, here's where we need to even think more. Because what if c can be less than or equal to 0? In other words, c becomes negative numbers. So if c becomes negative numbers, let's take a look. If c is negative, then our x vector is switched out this way. Well, when I add this vector when I add my c times x to my, for example, 1 times y, well, then what would I get? I would get this parallelogram here. And as I keep trying all of my negative c values, I get this entire line of solutions. And then as I start varying my d values, or just positive d values, I get this entire other quadrant. In the same way that we created the green and orange, we now create this entire purple region. And then we can continue this problem. And that's the thought experiment. As the next portion would be when c, and I should have written here, d is positive. What happens now if c is positive and d is negative? Well, to do that, you would clearly need another color of chalk, like maybe pink. So now if c is positive and d is negative,
A 0 on there.
oh, when I need a 0, I'm sorry, c is less than, greater than 0. So if d is negative, well, that switches y out this direction. And now I get the parallelogram formed by cx and dy. And pretty soon I filled out this entire quadrant. And if I try one more, the last piece, if both c and d are less than 0, I can now finish my picture. I can finish my picture, and I would have, what have I drawn? Well, those are almost the same color. Let's try, I'll just use green again, or orange again. I would soon have the last piece. I would have now covered the plane. And that's the big point, is that two vectors, and I'm going to put correct comma, not multiples of each other. Not multiples of each other. Form a plane. Okay? So that's all it takes. You have two vectors, you can form an entire plane. This little caveat, not multiples of each other. By that, what I mean is that if the vector y was a multiple of x, it would be something maybe right here. Well, in that case, then all I would have is a line. The vector y cannot be laying on x in order to create the plane. That's the one catch. All right, we have one more example. And I think what I'm going to do is we'll pause here. That was a big idea. And then in our next video, we're going to look at what happens when you move into